Good morning, everybody. Of course, we are not in Madeira. It's a strange situation. And I'll give you a short lecture on finite fracture mechanics and the coupled criterion. First of all, the question, what is finite fracture mechanics? Indeed, the best answer I got is due to Zvi Ashin in his paper of '96. It was in the introduction, he wrote, a spontaneous crack formation implies that new cracks appear in a very short time, and it is not possible or of interest to follow the history of their development. This is the main point. It is not either possible or of interest to follow the history of their development. It means that we have a first state, uncracked state, and then we have a final state with some cracks inside, and we would like to skip from the first state to the last one without details of the history of the development of the crack. And I'll show you that this can be done in some cases. First of all, a little history. Fracture mechanics in brittle or quasi-brittle materials deals with crack growth, okay? And here we are interested in crack nucleation. And of course, we are interested in brittle or quasi-brittle materials, and everybody knows that if we try to use Griffith's criterion to predict the nucleation of a new crack, it's not possible. Griffiths is not able to predict the onset of a new crack. And if we use another criterion like stress condition, we can have some troubles when there are very high stress concentration. So the history. We start with Inglis. Inglis indeed wrote a paper on the description of the stress field around an elliptic crack tip. Griffiths later, well-known Griffiths criterion based on the one hand, on the energy available in the structure, on the other hand, on the energy needed to create a crack. To create a crack consumes energy, and there is a balance in between these two quantities. Irwin finally settled a link between Williams' expansion and Griffiths' work based on the definition of the toughness and the equivalence between GC, the fracture energy used by Griffiths, and the toughness, the critical value of the stress intensity factor, as Irwin did. At the same time, the need to use two parameters emerged. Indeed, to define the length, and initially it was to define the distance at which a stress can be measured near a crack tip, because if you use the elastic solution, the stress tends to infinity when approaching the crack tip, so it's not possible to measure it close to the tip. And this Irwin, remember also his work on plastic zone, the size of the plastic zone, the length here, McClintock as well, and later Novozilov and Severin, who tried to use this length to predict crack nucleation at stress concentration point, especially at the sharp V notch. Okay, but the length was calibrated by the stress field at the tip of the crack. Novodilov used a point criterion, and Severin a line, an average along a line of the stress, but it's almost similar. Next, the coupled criterion finally emerges. that to do the same as that, but using the singular stress field, not only at the crack tip, but at any V notch, sharp V notch. It's singular as well. It's not the same singularity than for a crack tip, but it's singular. It means stress increases to infinity. And then we need some distance here again to be able to have a measure of the stress. The role of the generalized stress intensity factor, it generalizes the intensity factor introduced by Williams and Irwin. It's generalized because it's the Williams expansion not only for crack tip but for V notches. I can mention Carl Pitteri and the experiments by Dunn and co-workers. Finite fracture mechanics. I already mentioned the paper by Eschin in 96, but John Nairn and co-workers also wrote a paper in 93. And I have to mention also the book by David Taylor on the theory of critical distance. The couple criterion, it was introduced by myself in 2002. And I can cite a review paper by Philip Weisgraber in 2016. And what I can add is that the couple criterion was successful in many applications for many different materials, many different structures, and so on. And there is also some papers now, large number of papers comparing other approaches with the couple criterion, cohesive zone models, and the phase fill method. So now, what is the origin of the couple criterion? Indeed, during the 90s, we were using, as Sheen, as John Nairn, and many others, of course, as Griffiths did 80 years ago, we were using an energy criterion, but this energy criterion had a drawback. You can observe that if, always this problem of length, if you can extract a length, meaningful length from data, then you observe that all lengths larger than this one are still admissible lengths also for a crack. And this is what the problem, and we have to try to solve it and to think about it during the 90s. And finally, we proposed a solution in 2002. The first origin is these experiments by Pavidi and co-workers in England in 78. It's a cross-ply fiber, glass fiber reinforced polymer. You know, you have plies, outer plies here at what is called 0 degree. It means the fibers are parallel to the load here. The fibers here are parallel to the load, and inside there is a layer, a 90 layer, where the fibers are in this direction, orthogonal to the load. And in this kind of experiment, the first form of damage you can observe is a transverse crack in this layer. One transverse crack and many others if you increase the load. And these authors try to plot the strain, the applied strain at the onset of the first crack. And they obtain these black points here. You see, they are distributed in this way. And they propose a solution based on an energy argument to match with these points. And they propose this line. And there was at that time a very big controversy. People say this is not due to energy, this is viable because you know the inner layer is very thin, because here it's in terms of the inner ply thickness. If the inner layer is very thin, the flows are very small, and according to the variable theory, you have to increase the load to trigger fracture. Indeed, this controversy, Kelly gave a first answer in 88, and we propose to agree with everybody to say that both works and finally, in a way, are complementary. But anyhow, you need to use an energy condition to be able to describe this increase of the load when the inner layer becomes very thin. So this is the results by Parvizi and co-workers, and you see that it works quite well for here, for these points. But here it's far from perfect. And what we propose is to consider two conditions. The energy conditions here and a stress condition here. I mean that if the stress condition, if the tensile stress in the inner layer is above the tensile strength, then it fails. This is the reason. And you see that if we use these two conditions must be fulfilled. If the inner layers are very thin, then you start to increase the load, you reach the tensile strength, but it is so thin that finally there is not enough energy stored in the layer and not enough energy to create a crack. So you have to increase the load to give it value, to have enough energy. It is governed, this part, by the energy. Now, if it is very thick, it's different, it's very thick. First, you have enough energy to trigger the crack, but the tensile stress is not large enough, and then you have to increase up to the tensile strength to trigger the crack. So this is our idea. To settle their energy model, Parvizi and co-workers were using a shear lag model, and they showed that the change in potential energy between two states, no crack, one crack. We don't know how this crack grows, at which velocity, but no crack, one crack, okay? Before it's quasi-static. Once the crack appears, it's also quasi-static. Then we are able to calculate the potential energy with no crack, the potential energy with a crack with length equal to the inner layer thickness, and it's here it's the scaling coefficients proportional to the square of the load, the square of the inner layer thickness, and this is the width of the specimen. Because we are in plane strains, the assumption of plane strains, okay, this is irrelevant. The energy conditions now, this is a change in potential energy, and this must be larger than the energy needed to create a crack. It is the fracture energy GC, introduced by Griffiths, times the surface of the crack, it is E times D, okay? And from that, you derive that the first crack can occur if the applied stress is larger than this value. And you see that it depends on the thickness, and it is a decreasing function of the thickness E. Here, you see, it's a decreasing function. This condition is this blue line. Okay, this condition is the blue line. But you see, there is something strange. If E is very large, it can fail for small load. It's a problem. It's, for instance, this point. And now, if you add the stress condition, you see that this is no longer true because you have to reach the tensile strength before failure. Okay? So this, you have to add to the criterion this conditions, and you obtain finally the coupled criterion defined by this straight line. It is stress-driven failure, and if it's thin enough, this blue line, it is energy-driven failure, and there is a transition point here in between. But what can be seen is that at any time, for any thickness, the two conditions are always fulfilled. Here is the stress conditions that take precedence over the energy conditions, but of course, if you are here, you are far above the energy conditions. Here, it is the energy conditions that takes precedence, and of course, the stress condition is fulfilled. So the two conditions are fulfilled at any time. The transition thickness E0 plays a particular role below energy-driven failure, above stress-driven failure, and of course, here in this case, you see that this is the energy. You are still loading up to here to have a failure. It means that there are some extra energy that from an energy balance can be, for instance, a kinetic energy, waves, noise, and so on. Another interesting small test that originates a couple criterion is the failure of a bar in tension. You have a straight bar like that, and you pull on it, on the two face. Of course, what happens? The bar fails in two parts. Initially, no crack, you have potential energy. At the end of the experiment, it is broken in two parts, and there is no longer any potential energy. So the change in potential energy in between the two states is just the potential energy of the initial state, and it is defined like that, 1/2. This is the surface of the cross section. This is the length of the bar. This is the applied stress and Young modulus. Here, you get that. And now, again, if you try to use the energy balance, this is the available energy. This is the energy consumed by failure. It's GC, the fracture energy, times the surface of the crack, that is the surface of the cross-section of the bar. And then again, you get that it breaks if the applied stress is larger than this quantity. And it means that, again, if L is large enough, it can break for very small applied load. And this is of course, a paradox. But now everybody knows that for the failure of such a bar, it is the stress conditions that mainly govern the failure of the bar. It means that if you reach the tensile stress of the bar, it will break. It will break. And again, there is a transition length here that is defined by this quantity. This is not far from the length defined by Irwin. If you remove the coefficient 2 here, it is the length defined by Irwin, EGC divided by sigma c square. And I give here some example of this length for different materials. For alumina, it's 20 microns, for PMMA, 100 microns, but for limestones, it can be 7 centimeters, 7.5 centimeters. You know, it can become very large, depending mainly on the properties of the material, both the Young modulus, fracture energy, and tensile strength. If the bar is larger than the transition length, then we can calculate the extra energy. We call it, we suppose that it is kinetic energy in this case, and it is the change in potential energy minus the energy consumed to create a crack. You get this relationship, and even this we can consider multiple simultaneous fracture. Okay, and the condition is simply this inequality. In this case, it's not possible to decide if whether one. It's an open problem. Why? If the bar is very long and there is a lot of extra energy, it breaks in two parts and produce a lot of kinetic energy instead of. It's very difficult to decide. In some cases, when material that is going to fail is embedded in a matrix. For instance, it's the problem here of an inclusion embedded in a matrix in compression. Okay, in that case, of course, the part cannot spread far from the compression machine, from the machine. So you can have and can be observed multiple cracking, similar, but it's still an open problem for a bar why it breaks in general in two parts, not more. Now there is something interesting. If L is smaller than L0, okay, it means that for alumina, for instance, it means smaller than 20 micron. Okay, if it is smaller, then failure is driven by the energy. The load at failure is larger than sigma c, and it is very often interpreted as a strengthening of the material, and as can be met in micro or nano pillars, where the tensile strength that are observed, that are, from my point of view, apparent strength, are very high. It can be gigapascals and so on. So this is the applied load as a function of the bar length of the bar. And you see that if L is smaller than L0, this is larger than 1, and sigma A applied is larger than the tensile strength. Okay, so now let us start and try to introduce the couple criterion. There is a classical test that is a bending test on 3-point or 4-point bending on V0 specimens. If you try with sharp V0 at that moment, if you try to analyze this problem, either you use the stress criterion, I mean the tensile stress is larger than the tensile strength, and then this trigger fracture. But in that case, the tensile stress is infinite here at the tip of the V notch. So it means that as soon as you load it, very small load, it's infinite, so it breaks. This is not really realistic. But now, okay, we will use Griffiths. But if the V notch is larger than the omega is larger than 0, I mean this is not a crack, this is an open V notch, then you calculate the energy release rate introduced by Griffiths, you find 0, and then you conclude that failure cannot occur. And everybody knows that if you do this experiment, it breaks, but not for an infinitely small load. So the question, the main question, the coupled criterion try to answer. Now, so what is the CC, the coupled criterion? Sometimes I will say CC now. We start, just like Griffiths, from a very simple energy balance based on elastic solution. The change in potential energy between, remember the two states, no crack, cracked. This is a change in potential energy between these two states. The change in kinetic energy between the two states. The energy consumed by failure for a crank with length A. This must be 0. This is the energy balance. I am working in plane strain, some extension to 3D. Say some words in the conclusion can be considered, but we're in plane strain, so I omit the width of the specimen here. Now, if it is a quasi-static experiment, I mean, at the beginning, you load slowly your specimen, as it is done in many labs, then it means that this quantity is necessarily positive. There is no kinetic energy at the beginning. It could have kinetic energy at the end. So this is positive. And from this, you can derive immediately that from this very rough inequality, this one, that the change in potential energy with the minus sign must be larger than GCA. And this is the energy condition that is used in the coupled criterion. But you know here that there is here an unknown. A is unknown. It is the crack length, but it's unknown. Okay? And finally, the coupled criterion state that first, it should have enough energy to create a crack. This is this condition. And second, the tensile stress must be greater than the tensile strength all along the presupposed crack path. It means that before failure, along the crack path that is expected with length, unknown length A, the tensile stress must be larger than the tensile strength in order to trigger a crack. Remember, in the experiments, we have simple experiments by Parvizi on the cross-ply laminate or the bar in tension. This was fulfilled. And this is very important all along the presupposed crack path. You have to remember that because it permits to avoid sometimes some big errors, okay? It is a non-local condition. The condition must be, there is not a stress condition at a point, it's all along a line. As a consequence, this is not an assumption, the crack nucleation occurs abruptly. It means that at a V-notch, at an open V-notch, at the crack tip it's slightly different, at an open V-notch, the crack jumps. You know, it's almost impossible to control. Immediately you have a jump on the crack, okay? The crack jump from zero, no crack, to a length A, which up to now is still an unknown of the problem. So this is the coupled criterion in equations, inequalities, the energy condition, remember, and this is a stress condition, the tensile stress, Z is the distance to the tip of the V-notch, must be larger than sigma C, the tensile strength, all along the presupposed crack path, and still A is unknown, okay? What happens very often is that this function, sigma, is a decreasing function of Z. And in order to fulfill this inequality all along the crack, it is sufficient to fulfill it at the end of the segment, at mean in A, and it's enough, it's very often enough to write this point conditions. But remember, this point condition means that it is true all along the crack path. It is not a point stress criterion. So now we have two inequalities to solve, okay? How to do that? We will introduce here some, this G, energy release rate, was introduced by Griffiths. It says the derivative of the potential energy with respect to the length crack, to the crack length. And you see this is an approximation of the derivative. It's minus the derivative, okay? So this is an approximation of G. It's the derivative, and this is what we call incremental energy release rate, which is different from G, you see? It depends on A. Here, it depends, it doesn't depend on delta A. Indeed, it's a derivative, so it is the limit as delta A tends to zero. Numerically, you use this approximation, but indeed, Griffiths introduced a derivative which is independent of delta A. Here it depends, and it is an unknown. And you see that now there is a difference between the differential approach of Griffiths and the incremental approach of the CC. So, a short reminder, This is the conditions for crack nucleation. The incremental energy release rate must be larger than GC. And, okay, I write the point condition here, but remember the tensile stress is larger than sigma C all along the crack path, okay? And for the growth, now, if a crack exists with length A, then this crack will grow according to Griffith's criterion, which is written in this form. In general, sigma A is a decreasing function of A. On the other hand, G incremental of A is an increasing function of A. And this ensures that this system of inequality has a solution. You can, from this, in this general case, excuse me, you can calculate A from these two inequalities. We will see later how to do that. But indeed, remember that in general, it's possible to calculate A in this system. And in other cases that will be seen later as well, we have to discuss and to analyze case by case the solution. So now, what is the numerical procedure in order to implement the coupled criterion? First, you create a mesh without the future crack, okay? And you calculate the tensile stress along the presupposed crack path. You can have a question, but what is the presupposed crack path? In many situations, this crack path is almost known. We know, for instance, in the bending, three-point bending test on the V-notch experiment, we know that the crack starts along the bisector of the B-notch. So it's not, when it is not known, but we know at least at which point it starts, then we can try several directions and compare them in between in order to decide which direction is that of the crack. Okay, so initially a mesh without crack, and you calculate the tensile stress along the presupposed crack path. It means that after this first step, you know the function sigma of A. Remember, you know this function. Next, then along the crack path, you release the nodes. I mean, you unbutton the nodes. You open the crack. You unbutton one node, then this gives you a crack with a small length A1, and you calculate the potential energy for this small length A1, then you release the next nodes, and then you have a A2. You calculate the potential energy for this crack length A2, and at the end of the procedure, when you have unbuttoned enough points, the crack, you have to check a longer crack than the real one that will be computed less. But at the end of these two steps, you know from the first one this function, and you know from the second step this function. Then you can solve the inequality. Then you can calculate A and the load that is able to trigger the failure. And what is important in this approach, and this is a main difference between the coupled criterion and the other approaches I have mentioned, like cohesive zone models or phase field, is that this is a linear problem. You solve a linear problem here, and here you solve a sequence of linear problems. Okay, you release the first family of the first pair of nodes, one elastic calculation. You release the next pair of nodes, and so on and so on. So it's not really very expensive from the point of view of time consuming on a computer. Okay. Anyhow, you have no problems of convergence. Even if you need to make a lot of calculation, you are sure that you have no problems of convergence. It's pure linear elastic problems. Just one recommendation, if you try to implement the couple criterion using this approach, it's important to use the same mesh topology. You mustn't change the mesh in between the different steps of the computation. The first step where you calculate the tensile stress, and the next step where you release the nodes, it's the same topology of mesh that is concerned. There are two reasons. The first one, that it is easier than remeshing for each value of A, of course. But the main reason is that it avoids some error on the calculation of the difference of potential energy. Okay. So in this case, it is implemented. This quite. It works quite well. Many tests have been done in 2D and in 3D. It's interesting, and it works for any stress concentration point. If it is the sharp V notch, it works, but if it is not a V notch, but simply a circular cavity or something like that, there is no singularity, stress is not increasing to infinity, but you can use this approach. Okay, so there is another approach, which is not the one based on finite elements. It is the more mathematical tools using what is called matched asymptotic expansions. I will not discuss about this approach because this is at least a one-day course. To explain how does it works, but I will give you the results. This works provided it's asymptotic, so it means that somewhere there is something small. Here it is assumed that A, crack length at initiation, the crack jump length, it is small, and this is checked afterward. You do the calculation, you obtain A, and you check if it is small compared to the structure. If it is okay, it is valid. What you did is valid. If A is not small, it means that you cannot use this approach in that case. Okay, it is based on the Williams series at the tip of a V notch. Okay, here we are for a sharp V notch. At a sharp V notch, the elastic solution can be expanded in this way. This is a constant, irrelevant constant. This is what is called a singular term because lambda, the exponent here, is between 0 and 1. It means that if you calculate the derivative, the power becomes lambda minus 1. And you see that if lambda is smaller than 1, this is negative, and sigma increases to infinity if A decreases here. This is why it is called singular. This is not, the displacement itself is not singular, it is the stress field that is singular, okay? So it is based on this expansion of the elastic solution near the tip of a V notch, and from this expansion you can calculate the G incremental. It is expressed in this way. A is a scaling coefficient. It is not the same as the one we have seen for the bar intention. It's another scaling coefficient here that is a consequence of the match asymptotic expansions that can be calculated numerically. This is the only non-analytical term we need in general to calculate it numerically, but it can be calculated once and for all. And so this G incremental depends on the square of the generalized stress intensity factor here, K. Indeed, in this expansion, this term represents the intensity of the load, okay? Twice the load, twice K. So it appears K square, it means square of the applied load, and the crack length at the power 2 lambda minus 1. This is the result of the asymptotic expansion. This is the incremental. If you apply the Hooke law, constitutive equation for elastic material to this displacement field, you get the stress field, A at the power lambda minus 1. And if you need to go further, you can also calculate the energy release rate at the tip of a, now it's the energy release rate, the Griffiths energy release rate at the tip of a crack with length A, and you get this relationship, okay? And you see that, for instance, if there is no crack, the energy release rate G here, with A equal to 0, it is 0, okay? This is the reason why Griffiths criterion cannot work to describe the onset of a crack at the tip of a V notch if this V notch is not, of course, a crack if it is an open V notch. Now, it's easier because we have analytical relationships, then we can calculate A here. Just to recall you that you see that here sigma is a decreasing function of A because lambda minus 1 is negative, and as lambda is between 1/2, this is 1/2 is for a crack, 1 is for a straight edge, 2 lambda minus 1 is positive, so here we have a decreasing function, and here we have an increasing function, and with this condition we can solve the problem, and we can calculate A this way, and then we can calculate the critical value of the generalized stress intensity factor at failure, defined in this way. You see, what is interesting in this relationship is that if you have a crack, lambda is 1/2, 2 lambda minus 1 is 0, this term is 1. These conditions only involve GC. It is indeed the Griffiths criterion written under the Irwin form, because it involves GC, like Griffiths suggests, and the general stress intensity factor, but for a crack, the stress intensity factor is the stress intensity factor, so that you get that the stress intensity factor must be larger than K1C. It is, for a crack, it is called this way, and it involves GC. Okay. Now, if you have a straight edge, there is no longer any stress concentration. The V notch is completely open. The edge is straight. Lambda is 1. There is no singularity. Okay. Lambda is 1. Here, lambda is 1. Lambda minus 1, this is 0. You have just a stress that is a constant. It is the tensile stress parallel to the edge. If lambda is 1, you see that this is 0, this term is 1, and then this relationship involves only sigma c at the power 1. It is simply the maximum stress condition. You see, so this coupled criterion approach using match asymptotics fits with Griffiths for a crack and with the stress conditions for a straight edge, and propose a relationship for all the V notch opening in between. Of course, here we consider it's the simplest case, but we can also consider mixed mode loading, mixed between mode 1 symmetric loading and mode 2 an anti-symmetric loading. We can also consider blunted notches, and this approach using blunted notches is based also on match asymptotic expansions, but these asymptotic expansions are carried out with respect to the root radius of the notch instead of the crack length, but it can be done, but it's long. So now we are approaching the end of the presentation. This is the more classical case here. Here, this is sigma divided by sigma c, okay? And you get this decreasing function. This is the distance to the, for instance, classical case, the distance to the V notch here, A. The stress here, the energy conditions, it is an increasing function of A, and this is obtained for 80% of the force at failure. You see that the stress condition is fulfilled for A between 0 and this point, okay? And the energy condition is fulfilled far on the right of this figure, and there is no match. There is no common point which fulfills simultaneously the stress condition and the energy condition. So we can increase the load, and at 97%, we get this result. You see now that the stress condition is fulfilled from 0 to this point. All these points, precipitous crack path here, sigma is larger than sigma c, and the energy condition is fulfilled only from here to here. From here and other lengths on the right of the figure. This was, if you remember the beginning of the lecture, this one of the drawback obtained when using only an energy condition. Is that okay? If you use the energy condition, you can get one length, but as soon as you get this length, all the other lengths here are admissible lengths for failure, okay? And even if you consider the previous figure, this will cut the horizontal line somewhere here. It means that even for a small load, the energy condition, if the crack is enough long, the energy condition can be fulfilled. And this is a problem. But be quite, when Ashin and Nairn used the energy conditions, they were clever enough to be in some situation where it was the energy that governs the mechanism. Remember, there are some parts where it's the stress and some parts it's the energy. And what they did in their paper of the 90s is that they were both in the situation where it was energy governed, okay? So here, still no match. Admissible point from the energy condition point of view here, admissible point from the stress condition point of view here. So we still increase the load. Oh, sorry. And finally, we obtain this point. And at this point, both the stress condition and the energy condition are fulfilled. And the coupled criterion states that for this value of the load, where there is a first single point where the two conditions are fulfilled, this load is the load at failure. And what happens is that the crack jumps from here to here. There is a crack jump along with this length. Now, we have solved the inequalities with respect to A, and we can now calculate also the load at failure. But now, there is a crack with length, there is a crack with length A, 0 here, for instance, So, if there is a crack, I can refer to Griffith's condition to study if this crack will going on growing or not. And you can see that, so there is a crack with this length. I calculate G now, the energy release rate defined by Griffiths, and I find that it's far above 1. It's far above GC. It means that from that point, the crack grows in an unstable manner, okay? You see, finally, there are two steps in this initiation, a first jump, and then an unstable growth. And this is one reason to explain why it's very difficult or almost impossible to have experiments that allows to bring into evidence the length, this length at initiation. Because in this case, for instance, V notch, the crack jumps and grows in an unstable manner. It's impossible to observe experimentally that point, okay? So we'll move to the next situation. This is the situation of a thin layer. Remember that of the cross-ply laminate of Parisi and co-workers. And this is for a small load, you see. This is, in that case, the stress, tensile stress in the layer is a constant. Here it is smaller than sigma c, means that this line is not here. And this is the energy condition. And you see from the point of view of the energy condition, admissible lengths are from here to far on the right of the figure here. But you see that for these points, the tensile stress is not larger than the tensile strength, so no crack nucleation. Next step, we increase the load. If we increase the load, sigma becomes equal to sigma c. And in that case, you see that sigma does not really define a length. Now, all lengths here are admissible. Remember that the crack length is limited by the two outer plies. So this, in any case, this line is limited by the thickness of the maximum thickness of the inner ply. So here you see, this is the energy condition. If the thickness of the inner layer is larger than this value, then there is a transverse crack that can appear. And this is the right part of the curve of Parisi, you know, where it is stress, it is governed by the stress here. Because as soon as we reach the stress condition, failure occurs. But if the inner layer is thinner, I mean, it is in this region, you see that, for instance, for this thickness of the inner layer, the energy condition is not fulfilled. We are on the left part of the figure of Parisi, and if it is thinner, we need to increase again the load if the layer thickness is thinner. But in that case, you observe that the stress condition is far above the simple equality. Okay, so the two cases we have observed here. The first one, remember the V notch, and here, for instance, the inner layer of a close-ply laminate. Now, there is an interesting experiment that is often done, especially on the rocks. It's compression on drilled specimen. You have a specimen, there is a circular hole inside the specimen, and it is tested in compression. What happened in this specimen is that two cracks emerge from the north pole and south pole of the circular cavity. And it is stable. We will see that it is stable. The crack initiates, but at a time it stops. Okay, and we will see how it can stop. Here we are in a case where sigma c is low, tensile strength is rather low, and the fracture energy is quite high. This is, for instance, the case of a polymer. Okay, then as sigma c is small, you see that the stress condition is easily fulfilled. In this figure, it is fulfilled for every point of this line. But as sigma c is high, this ratio is small, and there is no match, okay, with the condition. And in addition, you see that, okay, it's an increasing function at the beginning, but that it becomes a decreasing function of the length. So we increase the load up to that point, and at that point, what we observe is that the two conditions are fulfilled. Okay, so the coupled criterion can state that the crack jumps from here to here, okay, for this value of the load. Then there is a crack now having this length. We can use Griffiths. But what is interesting in this case, when the incremental energy has an horizontal tangent here, it's very easy to show that G, in this case, is equal at that point. When there is an horizontal tangent here, G is equal to G incremental at that point only. You see, at the other point, it's not true. But at that point, is true. And you see that at that point, now we have a crack like that, but G is a decreasing function of the length. It means that it's a special case where the initial jump of the crack is also a length where the crack arrests. Okay, but indeed this requires some very special properties of the material. I think that we can have this situation in some rocks. And next, if you go on, then you have a stable growth of the crack, okay? You see, you have just to calculate G, and you see that G, as you increase the load, the curve that is here will grow like that, and then this point will move stably on the right. You have then jump followed by a stable growth, but quite seldom situation met in rocks only. Other situation here, now it's sigma C that is high, but GC is low. Typically, this is a case of ceramics. And in ceramics also, there's drilled specimen compressions are also tested, okay? So this, now you are familiar with this representation. This is the stress condition. This is the energy. And you see that there is some match here with the stress condition between this point and that point, but there is no match with the energy condition. So nothing can occur for that load. We increase the load. Okay, we increase the load and we reach that point. But you see, there is still no match. So again, the coupled criterion states that nothing occurs. Then we go on loading and we reach that point where now both the energy and the stress conditions are fulfilled. Okay, so now let us calculate the energy rate of Griffiths. And what we obtain is that it is above GC. So it means that the crack jumps, then has an unstable growth. But unstable growth up to here. Because here, you know, G Griffiths is decreasing and G becomes smaller than GC. This is the usual condition for an RS point. But what we have considered, you know, between this point and that one, all this surface here is extra energy. And a part of this energy can be used to grow the crack further. And in that case, what we observe is that the crack jumps, the lower bound where the crack cannot stop before that point because of G. And then now, if we consider the extra energy that is here, finally, this surface is equal to that one. The maximum length of the crack can reach is defined by G incremental equal to GC, which is also a decreasing function here. So the crack stops between these two bounds. But indeed, you know, very often it is this bound that is observed. We have some situation in ceramics where there are strong residual stresses where it is a bound in between these two. But indeed, we need here to have larger part of extra energy than this that is shown in this figure. So this concludes my lecture. I'm just in time. Where the CEC has been successfully applied in many situations. Blunted notch is an interesting problem, and here you have some references. Fiber debonding, references here, and So this is probably the first work, but the group of Sevi did many other papers following this one. Delamination of composite laminates, transverse cracking here. Even I think this paper, it was done in 3D. Damage in woven composite, different papers. Multi-cracking thin films. This is an interesting problem. The multi-cracking of thin and very thin films, where the coupled criterion works quite well. Crack deflation in layer ceramic, residual stresses, oxidized polymers. This is an interesting problem as well. Crushing of a pebble. This is a multi-cracking here in this case, like in thin films. And I recall you that it only requires linear calculations. Recent extensions, quasi-brittle materials. We consider damage at the tip of the notch, and then before failure, the material damage. This is the work we did with Zoe Yosivash. Small scale gilding, we're working on that now. But of course, we cannot at that point work with plasticity that spread all over the specimen. Only small scale gilding, I mean, the plastic zone remains small around the stress concentration point. 3D, there are many works now that try to apply the criterion in 3D. Some non-linearities, mainly the group from Darmstadt, work on that problems. And some efforts now have been used to propose some software in commercial codes. Okay, and at the end of the slides, I added a list of references, namely the references cited in these slides. And if you are interested, you send me an email and I can send you the slides. It's a PDF file. It's very easy for me. Thank you very much.